A very good morning, everyone. I am Dr. HimaBindhu, Assistant Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering. And my today's topic is degrees of freedom. Today we will be dealing about what is the importance of degrees of freedom, how do we calculate degrees of freedom, what is the use of an open and a closed chain mechanism, and what is exactly the requirement of the degrees of freedom in robotics. All that we'll be studying in today's session. What do we mean by degrees of freedom? Yes, what is degrees of freedom exactly means? It is nothing but degrees of freedom is an independent term where it is used for the independent movement of the wrist. Right? The degrees of freedom is nothing but it is an independent movement which is used for the wrist of a robot. Right? As we humans have the wrist for our hand, and it has some degrees of freedom with the help of which it is rotating in the rotary direction. Right? Whereas we don't have the wrist which is been moving in the vertical direction. Right? That is, any particular independent joint which is having certain movement in its wrist is known as degrees of freedom. Right? That is, the degrees of freedom is an extremely important factor. Right? The degrees of freedom is generally an extremely important factor in robotics that is used to define the physical motion of a robot. Right? Degrees of freedom is, without degrees of freedom, we cannot have the motion in our particular wrist or any particular hand or arm or joint in any particular joints or links. We cannot have the motion if we are not having the degrees of freedom. That is, it generally plays an important role in our part day-to-day life. Right? So the degrees of freedom is an important factor in robotics that is used to define the physical motion of a robot. Right? Generally, the robot is a combination of multiple mechanisms, as we all know. Right? The robot is a combination of multiple mechanisms where it is linked up with some links and joints, where the robot is being linked up with some links and joints. Right? So each joint has one degree of freedom. Right? For example, we are having a joint. This is the manipulator and this is the arm, for example. So this is the joint between the manipulator and the arm. Right? So each joint has its own degrees of freedom. Each joint is having its own degrees of freedom. Now, this particular degrees of freedom also depend upon the type of the joint. Right? The degrees of freedom also depends upon the type of the joint. And firstly, the 1 degree of freedom is generally used for a revolute, helical, and prismatic joints. Right? Generally, 1 degree of freedom is generally used for revolute, helical, and prismatic joints type of robot. Whereas a 2 degree of freedom Whereas a 2 degree of freedom is generally used for a cylindrical and universal joints. Right? Whereas the 2 degree of freedom generally occurs for a cylindrical and a universal joint. And the 3 degree of freedom is used for a spherical joint. Right? A 3 degree of freedom is generally used for a spherical joint. Now, there are generally 6 motions being occurred in a robot. There are 6 motions being occurred in a robot, where 3 are arm motions, and 3 are body motions. Right? Generally, for any particular robot, we have 6 motions being occurred, where 3 are the arm motions and the 3 are the body motions. Right? So, before we get into how to calculate the degrees of freedom of robot, we will be learning how these particular motions are occurred. Firstly, let us see how these particular motions are being occurred. So, for that, we will be drawing a diagram. Right? We will be seeing a robot. Based upon that, how the axis of rotation is being taking place in that particular robot, we will be seeing. So here, first let us draw a base, right? First let us draw a base, and to this we are linking up it. Let us first draw a robot, and let us see how this particular rotation is being taking place in this robot, right? So this is the radial direction. This is the vertical tra- traverse, and this is the rotational. This is the rotational traverse. This is the arm and body assembly. Right? And this is the wrist and wrist assembly. This is the wrist band. So this is the diagram of a robot. So in this we will be seeing how the motions will be carried forward. What are the 3 rotational motions and what are the 3 axial motions which we are having, that we will be seeing in this particular figure. So here we have a fixed base to which we have the arm and the body assembly being done. Right? This is the base which is being fixed, and to this particular base we have an assembly of a body and a arm, and this particular arm is being attached with a manipulator where we have a wrist, and at the end we have an end effector being fixed. So here we have various axis of rotations being taken, various motions being taking place. So initially this is 1, 2, 3, right? This is the 4, 5 and 6. So totally we are having 6 motions being taking place. What is the first motion? It is nothing but a rotational motion, right? The first one is a rotational motion, that is the arm here, whatever we are having, the rotational traverse is moving in a rotational direction, right? The arm, whatever we are having, to which the manipulator is being fixed, is moving in a rotational direction, that is in a rotational traverse. Whereas the vertical traverse, this particular manipulator, whatever we are having, the vertical traverse is moving up and down, right? It is moving up and down in the up and down direction, right? The vertical traverse is moving in the up and down direction, moving the manipulator depending upon the height of the object, adjusting the manipulator depending upon the height of the object. This particular manipulator is being moving in the vertical direction, whether it is up or it is down depending upon the height. Whereas the manipulator has an in and out movement also, in and out movement, right? Whereas the manipulator is also having the in and out movement, that is called as a radial movement. We can see here, right? In it is going in and out depending upon the requirement, depending upon the length to be covered. The manipulator is moving in and out of the arm with the help of the drives. Maybe it may be a hydraulic drive, or it may be a electrical driven drive, or it may be a pneumatic drive. So depending upon the drive, manipulator is moving in the radial direction in and out of the arm. Right? Next, moving on to the wrist end. Here we have one rotational axis being taking place. That is, this particular wrist will be moving in a rotational direction. The wrist bend is being moving in a rotational direction, whereas the yawn is also moving in the transverse direction. And this particular wrist is also moving in the rotational direction depending upon the requirement. So here totally we have 6 motions being taking place. Here totally we have 6 motions being taking place for any particular robot. Clear? Understood? That is, the degree of freedom is nothing but it is an independent movement. It is an independent movement of the wrist, right? A degree of freedom is nothing but it is an independent movement of the wrist in the three-dimensional space, right? In the three-dimensional space, the independent movement of the wrist which has been taking place for any particular robot is called as degree of freedom, right? So we have seen we have various number of degrees of freedom depending upon the type of the joint. So generally for a we will be having 1 degree of freedom for a revolute, helical and prismatic joints, and we'll be having a 2 degrees of freedom for a cylindrical and universal joint, and 3 degrees of freedom for a spherical joint. And here we have seen the 6 motions which have been taking place. Here we have seen the 6 motions which will be taking place for a particular robot in a vertical, radial, and rotary directions. Okay. So, how do we calculate the degree of freedom for any particular robot? For example, let us take a robot which is having 2 revolutionary joints. Right? For example, let us take a robot which is having 2 revolutionary joints and 2 prismatic joints. Clear? We are taking a robot which is having 2 revolutionary joints and 2 prismatic joints where all are independent without any dependency, where all the joints are independent without any dependency. Now, how do we calculate the degree of freedom for this particular robot? Totally, how many joints we have? 4 joints, right? That is 2 revolutionary joints and 2 prismatic joints. Totally 4 joints, where 2 are revolute and 2 are prismatic. So we are adding up that, right? 2 plus 2, 4. 4 into 4, right? That is, with each joint added 1 degree of freedom generally, joints are not all independent. right? The joints will, or whatever joints we're having, all the joints will not be independent, and some will have some constraints applied to them, right? So dependency of the joint further complexes the equation, right? When we have dependency being occurred in the joints, there will be some complexity being involved in that particular equation. So here we have come across the scientist called Kutzbach, where he have given a equation or derivation for this particular degrees of freedom, stating that each robo has a different mechanism, right? We all know each robo will be having different mechanism depending upon the application, depending upon the usage. The mechanism of the robo will be changing. So each robo has a different mechanism, and the calculation of the degree of freedom will also be different, right? And the calculation of the degree of freedom will also be different depending upon the type of the mechanism. But a common way of determining the degree of freedom for a robo is called as a Kutzbach criterion. Right? We have one common method with the help of which we can calculate, we can determine the degree of freedom, and that criteria is known as Kutzbach criterion. And, or we also can call it as Grubler's formula, right? Or we can also call it as Grubler formula. So with the help of this Grubler formula, we will be calculating the degree of freedom. Yeah? We have considered one example where we had two revolutionary joints and two prismatic joints, where it had its own independency of joints, movement of joints, and we've calculated the degree of freedom. Now, since each and every robo will not have the same mechanism, the degree of freedom calculation also will be different depending upon the mechanism. But in order to have a constant, or in order to have a standard formation to calculate the degree of freedom, the Grubler's formula have been introduced, and based upon that we will be calculating the degrees of freedom, right? So this is the formula to calculate the degree of freedom, where degree of freedom is equal to m into n minus 1 minus sigma I equal to 1 j c into I, where n is nothing but the number of links, right? N is nothing but the number of links of a particular robo, and j is the number of joints, right? N is number of links, j is the number of joints, and ci is the number of constraints provided by the joint I, right? Ci is the number of constraints which has been provided by the joint I, and Fi is the number of freedoms provided by the joint I. Clear? Fi is the number of freedoms provided by the joint I. And by on applying the Grubler formula for a planar mechanism, the equation for the degree of freedom will be equal to 3 into L minus 1 minus 2j minus h, where L is nothing but number of links, j is binary joints, and h is higher pair order, number of higher pair order. So in order to simplize, in order to give a simple formula for calculating the degree of freedom, the Grubler have given a simple equation where we are stating that the degree of freedom is equal to 3 into number of links minus 1 minus 2 into number of binary joints minus the number of higher pairs, right? So this is how we calculate the degree of freedom for a generalized robo, right? Now, when we take the degree of freedom for a 3-bar mechanism, we let us consider this as example 1, this as example 2, this as example 3, right? So when we are considering the 3-bar mechanism, how do we calculate the degree of freedom? Yes, how do we calculate the degree of freedom? The degree of freedom is calculated as 3 into It is a 3-bar mechanism. So the number of joints are 3. Right? 3 into 3 minus 1. What is our equation? 3 into L minus 1 minus 2J minus H. Right? 3 into L minus 1 minus 2J into H. This is the formula. Right? So substituting the values in this formula, what are we getting? 3 into how many links we have? 1, 2, 3. Right? How many joints are we having? We have j is equal to 3 and links. How many links are we having? 3 links. Right? So 3 into how many links we have? 3 minus 1 minus how many joints are we having? 3. So 2 into 3. We don't have any higher pair, so higher pair is equal to 0. So what is the degree of freedom for a 3-bar mechanism? It is nothing but 0. Right? That is, for a 3-bar mechanism, the degree of freedom will be equal to 0. Whereas when we take a 4-bar mechanism, here how many links do we have? 4. How many joints do we have? 4. So what is the link? 1, 2, 3, 4. How many links are we having? 4, right? 1 to 4, 4 to 3, 3 to 1, 3 to 2, and 2 to 1. So we are having totally 4 links. And how many joints we have? 1, 2, 3, 4. 4 joints, right? So 3 into 4 minus 1 minus 2 into 4, which will be equal to 1. So the degree of freedom for a 4-bar mechanism is equal to 1. Clear? Now, when we take a 5-bar mechanism, how do we calculate this? Yes. How are we calculating for a 5-bar mechanism? Yes. How are we calculating for a 5-bar mechanism? How many links or how many joints do we have? Yes. Again, here we are having how many joints? The joints are 5 and the links are 5. Right? The joints are 5 and the links are 5. So, how 3 into 5 minus 1 minus 2 into 5, where we are getting the degrees of freedom as 2. Right? Where we are getting the degrees of freedom as 2, again for a 5-bar mechanism. Whereas when we consider a 6-bar mechanism, when we are considering a 6-bar mechanism, what is happening here? How many joints do we have here? Yes, how many links and how many joints do we have here? The number of links is equal to 5 and the number of joints is equal to 6, because number of links is 1, 2, 3, 4. Right? 1, 2, 3, 4 and 5. And number of joints 1, 2, 3, 4, 5 and 6. Right? So the number of links is equal to 5 and the number of joints is equal to 6. So how do we calculate the degree of freedom? 3 into 5 minus 1 minus 2 into 6, which is equal to 0. Right? The degree of freedom for a 6-bar mechanism with 4 ternary joints will be equal to 0. Clear? So that is how we've calculated the degrees of freedom. Now the Grobler formula can be applied to any of those mechanisms that have 1 degree of freedom. Right? The Grobler formula can be applied. The Grobler formula can be applied for any to any of the mechanisms that is having 1 degree of joint. Now the joints which are forming the robotic system may be revolutionary or prismatic, or it may be helical, right? As I've told you, the 1 degree freedom joints are generally for revolute, prismatic and helical. So it does not apply the mechanism having 2 degrees of freedom or 3 degrees of freedom joints. Right? The Grubler formula is not being applied for the mechanism which is having 2 degrees of freedom or 3 degrees of freedom. Generally, the Grubler formula is being applied for only 1 degree of freedom joints, that is generally for a revolutionary, prismatic or a helical joints, whereas not for a 2 degrees or 3 degrees of the joint. So the formula can also be applied to open chain mechanism or closed chain mechanism, right? This particular formula can also be applied for a open chain mechanism, right? The formula can also be applied for an open chain mechanism. This is an example for an open chain mechanism. Why are we telling this as an open chain mechanism? Yes, how are we telling this as an open chain mechanism? Because the links whatever we are having is not we have one rigid link and remaining all are open, which have its independent rotation, right? Each and every other joint is having its independent rotation. It is not dependent on the other joint. So that particular type of the mechanism is called as the open chain mechanism. Whereas the links which are being attached to one another and they are dependent on the other links, that particular type of the mechanism is called as a closed chain mechanism. So generally for an open chain mechanism, will have 3 revolutionary joints and 1 prismatic joint. Right? Generally, for an open chain mechanism, we'll be having 3 revolutionary and 1 prismatic joint. Now, there are 4 links, bodies being connected for the 4 joints for the above figure. How do we calculate the degrees of freedom? How can we tell that it comes under 1 degrees of freedom and it is applied on a Grubler formula? How can we tell that, right? So degrees of freedom, as we know, it is the formula is 3 into L minus 1 minus 2 into J, right? So here, how many types of links and joints we have, depending on that we are calculating the degrees of freedom. So 3 into 4 minus 1 minus 4 plus 1, 2, 3, 4, right? So how many motions do we have? 4. 1, 2, 3, and 4. Where when we are calculating, we are getting the answer as 1. That is, the degree of freedom for an open chain mechanism is equal to 1. Clear? Understood? Now, moving on to the next mechanism. Here, this is also an open chain mechanism. Right? Now, how do we calculate why are we telling this as an open chain mechanism? Because each and every link is independent, right? Each and every link here is independent, and this comes under an open chain mechanism. Now, the Grubler formula is not applicable when joints are not independent. Clear? It is the Grubler formula is not applicable when the joints are not independent. For example, it is not applicable for a closed chain mechanism. And on applying Grubler equation, the above mechanism we get as the degree of freedom as 0. Right? That is 3 into 3 minus 1 minus 3 plus 1 plus 1 plus 1. We are getting the degree of freedom as 0. So, the Grubler formula will not be applicable for this particular mechanism. Right? The Grubler formula is not applicable for this particular type of the mechanism. But the above mechanism can be seen to be clearly having a degree of freedom equal to 1. But the middle joint in the above mechanism is not independent. Right? When this is moving only, when this is moving, automatically this should move, and when this is moving, automatically this should move. So this is not independent of its own. If the constraints are independent, if the joints are independent, then only the Grubler's formula will be applicable. When the joints are not independent and when the joints are dependent on the other, at that particular time the degree of freedom will be equal to 0, and the Grubler formula will not be applicable for that particular side of the mechanism. Clear? So Grubler formula does not apply to this particular type of the mechanism. Next, coming to the open chain and closed chain mechanism. This is a diagram, a figure for an open chain, and this is the figure for a closed chain mechanism. Now, how do we find out the degrees of freedom for this open and closed chain mechanism? It is finding the degree of freedom for any particular simple constructed robo is easy, right? Finding out the degree of freedom for a simple constructed robo is generally easy, and there will be no much dependent joints for that particular type of the robo. That is, there are more non-independent joints and more dependent joints which we are having. So the determination of the degree of freedom of a mobile robo gets more and more complex, right? When we are having more dependent joints than the independent joints, the complexity to calculate the degree of freedom will become more harder, more complex. It will not become easy for us to calculate the degree of freedom when we are having some dependent joints for the robo. When we have independent joints only, the equation becomes easier for us to find out the degrees of freedom. So. For simplicity, we can reduce most of the robotic mechanism design into open chain and closed chain mechanism. So, in order to reduce that particular defect, in order to reduce that particular complexity, we will be simplifying the robotic mechanism design into open chain and a closed chain mechanism. Yeah, in order to reduce the complexity in the design or structure of in order to calibrate the degree of freedom, we are dividing the robotic mechanism into two different forms, that is open chain and a closed chain mechanism, right? Where we all know that the robot with a 1 degree of freedom joint has only is applicable only for revolute, prismatic, and a helical joint. The degree of freedom will become easy using the Wigner formula for that particular type of the links. Right? For that particular type of the links, the Wigner formula will become easy. Now, as the robot involves non-independent joints, dependency and 2 degree and 3 degree joints, the calculation gets more complex as we have already discussed, right? When we have 2 or 3 degree of freedom, the calculation will become more complex. So, when it is becoming more complex, we are converting it into open chain and the closed chain mechanism. In order to reduce the complexity, in order to reduce the equation complexity, in order to have a fast calculation to know the degree of freedom, we are dividing the robot mechanism into into two different mechanisms as open and closed chain mechanism. Yeah. So why degree of freedom is important? We have discussed about degree of freedom, calculation, how we have calculated all that. But we have to know why this has been important, right? What is the main importance of this particular degree of freedom to calculate? So the degree of freedom is an important consideration in determining the ability of the robot, right? In order to determine this, we have to remember ability. In order to determine the ability of the robot, the degree of freedom calculation, degree to know the degree of freedom is very important. Right? So different tasks require different range of motions. As we all know, some tasks may require rotational motion, some tasks may require a vertical movement of the end effectors on the manipulator, or some tasks require some other orientation. So different tasks requires different range of motions or approach of angles or any particular orientation. So in order to simplify that, simpler tasks can be accomplished by lower degree of freedom tasks. In order to simplify that, in order to simplify the task, we can accomplish the lower degree of freedom task, which while more complex tasks require higher degree of freedom. Right? For a simpler task, we require lower degree of freedom, and for a complex task which we have, we will be requiring a higher degree of freedom. That is the movement of the wrist. As I've told you, degree of freedom is nothing but the independent movement of the wrist, which is used to perform the tasks. So here, when we have smaller tasks to be done, for example, we need to pick a particular pen from one place and to move it to the other. That doesn't require more complexity. That doesn't involve more complexity of the movement. So there, the lower degree of freedom is sufficient. But at the same time, when we have a complex product to be material handled, so there we require higher degree of freedom, where the number of motion axes will be more. So there we will be have for complex tasks we will be having higher degree of freedom, right? Plus, the degree of freedom of a robot is again an important factor in determining the working space of the robot, right? The degree of freedom of a robot is again an important factor in determining the working space of the robot. That is, for example, we have a small industry and we have a large scale industry, right? And in this particular small scale industry, if we are having a higher degree of freedom robo, will it be will the work whatever this particular robo is doing can accomplish the overall space? No, it cannot be applicable. And for a higher larger industry, if we are taking a smaller robo with a single degree of freedom, will it be possible? No. So, depending upon the environmental condition, depending upon the type of the industry, also the robo selection will be done. That is, the higher degree of the robo, which is having a higher degree of freedom, will be considered for a large working space, and the robo with the smaller degree of freedom will be applicable for a small scale industries for doing minor works, right? Therefore, the degree of freedom is important for determining the reachable working space and accessibility to the object in the reachable workspace. Clear? A higher degree of freedom robot not only has a larger working space, but it also utilizes the available working space more efficiently. That is, when any particular work is to be done with more effective, more efficiency, and more accuracy, there in the large scale industries will be using a larger degree of freedom robots. Clear? Yes, understood about the degree of freedom. So, degree of freedom is nothing but it is an independent movement of the wrist, which has been occurred in a robot arm, is known as a degree of freedom. And the degree of freedom is being calculated with the help of the Rubler formula, which is being stated with a scientist called Rubler, and he have given that particular equation, and with that particular equation we will be calculating the degree of freedom for any particular robot. Okay, so this is all about the degree of freedom, and in the next class we will be studying, or we will discuss about the accuracy, relatability, and precision of the particular robot. How what is the importance of accuracy? What is the importance of repeatability or precision movement of the robot? All that we will be discussing in the next class. Thank you. Signing off for today, Dr. G.
Like, share, and subscribe. Hit the bell icon for more updates.